The human eye does a tremendous job of allowing us to view the world. Sometimes we want to observe phenomena beyond the scope of the human visual system. For example, capturing infrared images and falsely coloring them to appear relevant to the human eye. Or using a microscope to reveal details much smaller than the human eye can see. While a microscope is good at observing small details, details such as small motions or changes in an object over time can still go unnoticed. One such example, while not normally visible, a person's face actually changes color over time as blood flows in and out. Another use is observing the vibration of an object, from a guitar string to the shaking of a crane. The method presented here gives us a technique to amplify these minute motions to make them easily perceptible to a standard viewer. So let's take a closer look at Eulerian video magnification. The basic steps involved include spatial filtering to reduce noise, temporal bandpass filtering to isolate motion, amplifying said motion, and then reconstructing the final enhanced video. Before we get into the full method, however, let us first consider the basic math behind video magnification. First, there are two different ways we can track motion in 3D space: Lagrangian or Eulerian flow. Lagrangian flow is observed by tracking the change in position of a specific object over time, like a boat floating on the waves. Amplifying this type of motion is useful for increasing small points of movement. In Eulerian flow, a specific location is observed, and the change of flow in that location over time is noticed. The Eulerian method specializes in amplifying small changes in smoother structures. There are good methods that work using Lagrangian flow, but they involve more information about the specific points that need to be tracked. In this case, the Eulerian flow was used by looking at the change over time at each pixel location. Here we have a 1D example of the math used in this method. Intensity can be modeled as a function of both location and the time, and the motion of an object can be modeled as a displacement due to the time. So, the goal of video magnification is to amplify this displacement, making the intensity be much greater than the original. Looking at the functions, we want to isolate the time component from position component, which we can do by using a first-order Taylor expansion approximation. Looking at the blue and red lines, you can see that the approximation works fairly close to the original. Then, by applying a properly designed bandpass filter, we can isolate the change over time. By amplifying this band, we get approximately the amplified function we want. However, before we magnify these motions, we first want to use spatial filtering to reduce the noise. Without the filtering, the noise will be wildly amplified, making the video unrecognizable. So an image pyramid must be calculated for each frame in the video. A Gaussian pyramid works by applying a Gaussian blur to an image and then reducing the size to a quarter of the original. A Laplacian pyramid works by taking a lower level of the Gaussian pyramid, expanding it back up, and then taking the difference between the blurred and the original frame, leaving the edges of the object. By looking at the Gaussian blurred image, we can accurately enhance the change in color over time, while looking at the Laplacian image, we can enhance the edge movement. And the pyramid can be calculated to different levels. The larger the level, the smaller the image, and the lower the noise. So most of the magnification needs to occur at the bottom of the pyramid. Once the spatial filtering has occurred, then we get into applying the bandpass filter. The Fourier transform of the data at a pixel location over a period of time is calculated, and then the bandpass filter is multiplied to isolate a specific set of frequencies. The result of this is then taken the inverse Fourier transform of to get the data back into the spatial domain. In the example shown here, an ideal bandpass was used to get a fully amplified specific known frequency, such as a heart rate. or a string vibration. For more general vibrations, such as a building shaking or a person moving, a Butterworth or a similar wide bandpass filter is more useful. Once the motion has been isolated, an amplification factor is multiplied to the motion based on the level of spatial filtering and then added back to the original at that level. Finally, the final video needs to be reconstructed by taking the smallest level of the pyramid, expanding it fourfold to the next level, and adding it up. The output video will have clearly defined amplified motion. So first, we attempted to get a pulse from the blood flow in a person's face. Looking at the original video, it almost looks like a still image. Once magnified though, the color in the face pulses clearly between yellow and dark red. You can also notice there was some movement that was magnified as the face seems to jump back and forth. All of the amplification was done on the lowest level of the pyramid as to reduce this motion magnification and only really show the color changes. The frequencies magnified were between 50 and 60 beats per minute, or 0.833 to 1 Hz, and the change was amplified 100-fold to make it easily visible. Next, a guitar string was captured and amplified. Looking at the output, the lower E string definitely shows large movement, and also is amplified more in areas of high contrast, such as the dark string on the bright guitar, not the string over the hole. Also, from this example, you can clearly observe an increase in motion noise all throughout the scene, although visibly we are still able to distinguish the motion of interest. For the low E on a guitar, the vibrational frequency is 82 Hz, so we magnified an area between 72 and 90 Hz by 50. All the amplification was done in the Laplacian levels to amplify movement of the string and not color changes. For the other strings, we could change the frequency to match the specific note and amplify that motion instead. Next, an attempt to get a pulse from a cell phone video was tried. Looking at the output, some color change is noticeable. However, the vibration of the camera and video compression seem to create a lot of artifacts. For the video, a typical resting heart rate was considered, and the amplification was only 30 to try to reduce the artifacts seen in the video. The shaking motion is more highly magnified, making the output data harder to decipher. Finally, we attempted to get a pulse by looking at the motion of a vein in the wrist rather than the color changes. There is still some slight motion magnification that we aren't interested in, but by looking in the correct vein area, we can clearly see the pulse going in and out. Again, the typical heart rate frequencies were amplified. In this case, we amplified the Laplacian levels to see the motion change and not the color change. To conclude, Eulerian video magnification is a useful technique for observing the hidden movements of the world. To create useful output, a process of spatial filtering to reduce noise and temporal filtering to amplify the information is used. To obtain good results, the frequency of the wanted motion must be known, and the camera and the object must be stable to reduce extraneous motion magnification. And the future for video magnification is bright. The method has uses in a variety of areas, such as the medical field, product design, and structural analysis.